welcome back to this 9th class of the NPTEL course on principles of polymer synthesis. We have been discussing the topic of step polymerization, the principle of step polymerization, and in this class we are going to continue with that. So, in the last class the point where we left you is the talk of the molecular weight distribution. So, I told you that there is a statistical approach that you could use in order to find the distribution, the number fraction distribution with respect to the degree of polymerization or the weight fraction distribution of the different species that are present in the polymer sample as a function of the degree of polymerization. So, degree of polymerization is nothing but the average number of structural units per polymer chain, again as I am telling you. This is directly correlated with the molecular weight. So, you multiply the degree of polymerization with the average molecular weight of the structural unit, and then you get your average molecular weight, which might be a number average molecular weight or weight average molecular weight. We will come to that in a little while. So, let us then begin our discussion today. So, what we are looking for is to derive an expression for the molecular weight distribution or derive expressions that give you a fair bit of idea of that. So, for that we are going to use a statistical approach. Fleury's statistical approach, and of course, this is going to assume equal reactivity of functional groups. The same assumption that we had made when we analyzed the kinetics of these reactions. So, let us begin with two bifunctional monomers like this AA and BB, and the assumption is that we are taking stoichiometric amount. So, most of the times this we typically take stoichiometric or near stoichiometric amount in practical situations also. So, we begin by asking the following question. Say the reaction has progressed up to a time t. So, at time t, what is the probability of finding a polymer with X structural units? So, the polymer is growing with time. The question that we are going to ask is that suppose the reaction has progressed up to time t. So, at this point of time, what is the probability that we will find a polymer that is having X number of structural units? So, as you know, we are looking at averages. So, when we are saying that we are trying to find a polymer with X number of structural units, that would also mean that all the polymer chains that have been produced up to that time, all of them do not have the same number of structural units. Some of them have X number of structural units, some of them has say Y number of structural units, some of them have say Z number of structural units, so on and so forth. That is why the concept of average comes. You have polymer chains of different lengths. Now, how different the lengths are, that is another question, that is given by the distribution of the molecular weight. If you can control it more precisely, that means if your polydispersity index is closer to 1. So, the closer to 1 it is, the more evenly distributed, the more uniform the lengths of the polymers are, but it is another thing that you cannot actually control the distribution beyond a certain limit in certain polymerization reactions. This is a very vague statement that I am making, you might be thinking, but hopefully after I have finished this analysis, it will give a justification of this kind of statement, that you cannot control the molecular weight beyond a certain, control the distribution of the molecular weight, to be more precise, beyond a certain limit. I mean, which actually means that the PDI or the polydispersity index, which is the ratio of weight average degree of polymerization to the number average degree of polymerization, that ratio you cannot sometimes control beyond a certain limit. You want it to be 1, right, all the polymer chains to be of same length, but in reality for certain class of polymerizations, especially say we are talking about say step polymerization, you cannot go to 1, it will be higher than 1, it will in fact be close to 2. You cannot go to lower than, so you cannot go to say 1.5 or close to 1, it will be close to 2. Those reasons we will be discussing here. After this analysis it should become clear. So, at time t, what is the probability of finding a polymer with x structural units? So, in order for this situation to unfold, what should happen to the A functional units? For a polymer of x structural units or an x mar to be produced, you basically need x minus 1 number of A groups to react. So, when you have formed an x mar, actually to form the x mar, x minus 1 number of A groups have reacted and 1 A group remains unreacted. In the x mar, in the formation of x mar, in the process of formation of x mar, x minus 1 number of A groups have reacted and 1 A group remains unreacted. Let me explain this thing little bit more. Say you are reacting ethylene glycol with adipic acid . Okay. So, first reaction will produce, so this reaction of alcohol with carboxylic acid will produce a dimer like this OCO CH2 whole 4 CO2H. Now, let us say this particular molecule reacts with, so this is a dimer, let us say this reacts with another molecule of ethylene glycol. So, it will react here. So, what will be the product? OH CH2 CH2O CO CH2 whole 4 COO CH2 OH. So, you have created a trimer. So, in this trimer how many structural units are present? This is one structural unit, this is a second structural unit, this is a third structural unit. So, it is a trimer, it has 3 structural units, it has 3 structural units. Let us say this ethylene glycol I am terming it as the monomer AA in accordance with this, and adipic acid as the monomer BB. So, in the formation of an oligomer in this case with 3 structural units, how many A groups, that means how many alcohol groups have reacted? So, in the first step 1 alcohol group has reacted. So, this alcohol group has reacted in the first step. In the second step another alcohol group has reacted. So, basically in order to create 3 structural units 2 alcohol functionalities have reacted, and how many alcohol functionalities remain unreacted? how many alcohol functionalities remain unreacted? One alcohol functionality remains unreacted on this side, for example, here. So, in this particular scenario then, in order to create the 3 structural units here, if you are looking at AA, so you have 2 number of A groups that have reacted, 1 number of A group that remains unreacted. So, if you, I mean this is just a comparison to tell you. So, if you are looking at, for example, if you looked at this as AA or this as AA, the similar situations would arise. Now, so x minus 1 number of A groups have reacted and 1 A group remains unreacted. So, what is the probability that 1 A group has reacted? Let us say P is the extent of conversion, in keeping with whatever we told before. Let us say P is the extent of conversion. So, P can also be termed as the probability that 1 A group has reacted. So, P can be also termed as the probability that 1 A group has reacted at time t. Everything is at time t. So, this is the probability that 1 A group has reacted at time t. So, what is the probability that 2 A groups have reacted at time t? That is P into P equals to P square. Now, why it is P into P and not P plus P? Now, this is P into P because these events are independent of each other. Why these events are independent of each other? Since the reactivity of one functional group does not change when the other functional group has reacted. So, this is independent of each other, these 2 events are independent of each other, and when we are looking at probability of 2 events occurring simultaneously, if the 2 events are independent of each other, then the total probability is basically a multiplication of their individual probabilities, it can be shown. So, probability that 1 A group has reacted at time t is P. So, probability that 2 A groups will react is P into P is P square. So, probability that x minus 1 A groups have reacted is P to the power x minus 1, but 1 A group has not reacted. So, what is the probability that 1 A group does not react? That is 1 minus P, because the probability that 1 A group reacts is P. So, the probability that 1 A group does not react is 1 minus P. So, what is the probability that all these events, so ultimately what is the probability that all these events occur simultaneously? Because you have to look for probability of finding the x mar. So, the x mar will be produced when all these events occur simultaneously. That means x minus 1 A groups have reacted and 1 A group has not reacted. So, what is the probability of finding an x mar? Now, because these reactions, these probabilities are independent, these events are independent, again there will be multiplication. So, there will be multiplication of 1 minus P with P to the power x minus 1. So, that is the probability of finding an x mar, and this is nothing but the number fraction or mole fraction. So, let us say small n x is the number fraction that will be equal to, so number fraction that will be equal to 1 minus P into p to the power x minus 1. So, this is something that gives you the variation of the number fraction with respect to the x, which is the degree of polymerization, because x average x structural units. So, if you have a polymer with x mark, that is having a degree of polymerization of x. So, small n x is the number fraction distribution. So, small n x, if it is nothing but number fraction or mole fraction, that will be equal to capital N x by capital N, where capital N x is basically the total number of polymer molecules which have x number of structural units, and capital N is total number of polymer molecules. So, capital N contains all the polymer molecules which have different number of structural units. Capital N x, because x is a subscript, capital N x tells you that this is the number of polymer molecules which have x number of structural units. So, this ratio will give you the mole fraction of polymer molecules or the number fraction of polymer molecules with x number of structural units, with x number of structural units. So, that is equal to 1 minus p into p to the power x minus 1. Now, what is capital N? We know the value of capital N is nothing but n0 into 1 minus p, where p is the extent of conversion, n0 is the total number of molecules to start with. So, if you put those values here, then your nx is nothing but n0 into 1 minus p square into p to the power x minus 1. So, this is the main expression. So, this is the number fraction distribution. This equation gives you number fraction distribution as a function of your degree of polymerization. So, number fraction distribution. So, what is the weight fraction distribution? What is the weight fraction distribution? Let us say I put small w x. So, basically let us say weight fraction small w x is weight fraction of x mar, just like the number fraction of x mar. So, weight fraction of x mar is nothing but equal to total weight of all x mars divided by total weight of all molecules, that is a fraction, weight fraction in this case, which is nothing but total weight of all x mars. So, what is the total number of x mars? That is nx. Each x mar contains x structural units. So, multiplied by x multiplied by m0, where m0 is the molecular weight of the structural unit. So, total weight of all x mars is nothing but nx into x into m0, because what is the total number of structural units that we are dealing with? That is x into nx, because nx is the number of molecules which each of them have x number of structural units, and what is the total weight? That is multiplied by m0, because m0 is the weight of one structural unit. So, what is the weight of nx into x number of structural units? That is this, which is total weight of all x mars divided by total weight of all molecules. So, you sum it up over all x, all the x's, because x can be of different values. So, when you are talking about all the molecules, you are actually encompassing molecules with all different number of structural units. So, that is this. So, m0 goes, so this is nothing but nx into x divided by sum over nx into x, and this is total weight of all the molecules was this. Now, what is the sum over nx into x? Sum over nx into x is nothing but n0, because you are actually summing up all the number of molecules here, and this is nx into x. Now, this nx by n0 already you know from the previous. So, this nx by n0 is nothing but 1 minus p square into p to the power x minus 1. So, that if you put there, your wx becomes x into p to the power x minus 1 into 1 minus p square. So, that is the final expression of weight fraction of x mar. So, if you now, so here I am also putting the number fraction distribution 1 minus p into p to the power x minus 1, that is the number fraction distribution. So, if you plot this number fraction or nx as a function of x, that is the degree of polymerization, and you are actually multiplying by some factor, say 10 cube or something like that. So, you are multiplying by some factor. I am not putting the values here, say 10, 20, 30, so on and so forth. Just want to give you in principle the understanding of that, say x is 100 here, x is 200 here. So, what you will have is something like this. So, I am going to draw certain things for you, and then I will explain to you what they mean. So, I am going to draw this graph, and then I will draw something like this, and then thirdly, so let us say this is curve 2. I will draw something like this. Let us say this is curve 3 and this is curve 1. So, these 3 curves, you know, here is p also in this particular expression. So, these 3 curves, there are different values of the conversion, that is p. So, the first curve is for p equals 0.96, 96% conversion. The second curve is for theoretical, p equals to 0.9875, around 99% conversion, less than that, and the third curve is for p equal to 0.9950. So, what this graph tells you is that, so if your x is equals to, say, if you are looking for an explanation of this graph, that is right there, as you go further and further down the graph. So, this graph, this graph, this graph. So, this graph is for a lower conversion, lower extent of reaction. This graph blue is for a higher extent of reaction. This red curve is for even higher extent of reaction. So, and this number fraction, this corresponds to with respect to the degree of polymerization here. It tells you, this graph tells you, say for example, the graph 1, this tells you that at 96% of conversion, this is the number fraction distribution of different oligomers or polymers, oligomers, everything. So, that means if you are going towards here, you are going towards a monomer. You know, x is very small, oligomers or even monomers when it is getting very close to the y axis, and this is the amount of monomer that will be present at p equals 0.96, and then say for example, this is the number fraction, this is the number fraction of 100 mar, so on and so forth. And even when you have say 99.5% of conversion, this is the number fraction of the monomer that will be remaining, which tells you that you will at all point of time, regardless of the extent of reaction, you will have more number of monomer molecules in terms of number, more number of monomer molecules than any other polymer species. So, this may appear to be little bit counterintuitive to you, but this is what we will actually get here, and it is also verified afterwards. I will tell you how the full theory is verified in one way or the other. So, this graph actually tells you, so the graph falls like this towards higher degree of polymerization. So, at the lowest degree of polymerization, you have a value of number fraction that is higher than any higher value of degree of polymerization than xn equals to, so 1. So, that means at any extent of polymerization, even if it is 98%, 99%, 99.5%, if you just look at the numbers of different species present, the number of monomer molecules, the number of dimer molecules, the number of trimer molecules, the number of tetramer molecules, the number of monomer molecules is the highest among all the polymer species. What about the weight? This is the number. So, what about the weight? So, if you look at the weight fraction, so you are plotting Wx as a function of x. So, what you will get is the following. So, this is for curve 1, again 1 corresponds to this. So, approximately, so this will be like 100, this will be like 200, 300, so on and so forth, and this will be for curve 2. So, like this, so curve 2 corresponds to this, and this will be for curve 3. So, weight fraction. So, if you are looking at the basis as the weight, here the basis was number. So, the number of monomer molecules at any point of time for the polymerization is the highest with respect to all the other polymeric species. Here, if you look at on the basis of weight, the proportion of low molecular weight species, this side is the low molecular weight species, this side is the higher molecular weight, because X is the number of structural units. So, proportion of the low molecular weight species is very small. So, if you are looking at curve 1, so at 96% conversion, weight wise the proportion of 100 mer, say for example, if you look at this graph, the proportion of say 100 mer, it is the highest. Or if you are looking at curve 2, which is 0.9875, 98% conversion and close to 99% conversion, the proportion of somewhere between 100 and 200, that many structural units will be there per polymer molecule, the proportion of those species in terms of weight is the highest, and this maximum roughly corresponds to the number average molecular weight. So, this is the difference. So, these two curves tell you that the number fraction of the monomers is the highest, no matter what is the extent of polymerization. However, in terms of the weight fraction, it is the different issue. The weight fraction of the low molecular weight species is very, very small. So, even if the number is the highest, the weight wise the contribution to the total sample is very, very small, and the contribution to the total sample in terms of the weight is maximum close to the number average molecular weight value. So, some of these graphs can be verified because you know this kind of distributions we could experimentally get, say the molecular distributions we will get from the GPC curve and all, but something that echoes with this particular class in a very simple way we can also verify. Say let us say what will be the value of Mn, we will go to the expressions here, what will be the value of Mn, that will be xn bar into m0, we have already talked about that. What is the value of xn bar after all these analysis, what is the value of xn bar we will get? Let me write down first and I will explain to you. That is this. This is a number fraction of x mar and this is the number of structural units. So, this is basically, so this x is your degree of polymerization and here, so this is the degree of polymerization, this is number average degree of polymerization, and so when you are averaging this, basically you are averaging, you are weighing this particular thing with a number fraction. So, basically this is also the concept of average. Let us say when you talked about the expression of Mn, that was summation Ni Mi divided by summation Ni, if you remember. So, this is basically nothing but you can also write it down as, let me say capital N, I mean it depends on the symbols that you are using, you can use different symbols as long as you know what the symbols are. Let us say capital Ni into Mi. So, this Ni is basically the mole fraction, this is the mole fraction. So, you could also write this as summation of mole fraction into the corresponding molecular weights, the same way that you have written the MW, which is the summation of weight fraction into molecular weight. So, you are weighing the molecular weights with weight fraction and then you are getting the weight average. You are weighing this with weight fraction and that gives you weight average. You are weighing the molecular weight with number fraction, that gives you the number average. So, you are weighing the molecular weight to get an average of molecular weight. So, here you are weighing the degree of polymerization to get average degree of polymerization. So, when you are weighing the degree of polymerization with number average with the number fraction, then you are getting number average degree of polymerization. When you are weighing the degree of polymerization with the weight average, then you get weight average degree of polymerization. So, the same concept of average. Okay. So, this is the number average degree of polymerization. So, summation of the number fraction into x over all x's. So, if you put the corresponding values here, that becomes x into p to the power x minus 1 into 1 minus p, and that is equal to 1 plus p square, so on and so forth, and this can be approximated as 1 divided by 1 minus p. And similarly, if you are putting all the values here, that will be sum over x square into 1 minus p square into p to the power x minus 1, that will be equal to 1 plus p divided by 1 minus p. And now, what is the polydispersity index? Polydispersity index is nothing but mw by mn, and mw is basically xw into m0, mn is basically xn bar into m0. So, the number average degree of polymerization into molecular weight, average molecular weight of the structural unit, and this is weight average degree of polymerization into average molecular weight of structural unit. And again to repeat, when you are looking for degree of polymerization average, you weigh the corresponding degree of polymerizations with the corresponding number fraction. When you are going for number average degree of polymerization, you weigh the x, that is the degree of polymerization, with corresponding weight fraction when you are going for weight average degree of polymerization. So, if you put those values here, ultimately what you will get? You will get 1 plus p. P is the extent of conversion. Surprise, PDI is nowhere near 1. As I told before, you need a very high value of p in order to get molecular weight of any importance as far as the practical utility is concerned. So, p has to be as close to 1 as possible for your purpose. So, if p is, so p can be 1 or less than 1. So, if p is 0.5, does that serve your purpose? No. You look at the xn bar value, the number average degree of polymerization is extremely low. You only have oligomers, does not work for you. You need at least 99% of conversion. Go close to 1. So, that means your PDI or polydispersity index can never be close to 1. So, the maximum value of PDI can be 1 plus 1 equals to 2 when p equals to 1, and it has to be close to 2. Whether you desire it or not, it has to be close to 2, because in other ways, because otherwise you cannot get high molecular weight polymer. That is your first priority, to get high molecular weight polymer, and then your PDI is automatically close to 2. So, of course, then there is a way to find out if this theory is right or wrong. Try to find out the PDIs from the GPC, for example, or some say use the suitable standard for calibration, and try to find out the PDIs for different state polymerizations, and you will see that many of them are close to 2. In fact, they are sometimes more than 2, like 2.2, 2.3, so on and so forth. There are reasons for that, that if you have impurities present in the sample, because the impurities that change the number of particles in the system, that have a greater effect on the value of Mn, that is the number average molecular weight, that will reduce the number average molecular weight, and correspondingly your PDI will go up, so that will be higher than 2. So, in practice, for many step polymerization reactions you get close to 2. So, that serves as a validation for this theory. It has not been validated for all the reactions, but for many systems it has been found that this particular theory has a sound basis. So, what we will do is that we will do a small problem, very small problem, just we are going to use the formula, and this will give you an idea of how to tackle some of these different simple questions. Let us say you are asked, what is the weight fraction of trimer? What is the weight fraction of trimer in a step polymerization that is carried out to 99% conversion? So, what is the weight fraction of trimer in a step polymerization that is carried out to 99% conversion? I mean, these are the utilities. You have done the reaction to a certain extent, and then you want to find out what is the weight fraction of different species. You can find out using some of these equations. So, what is the equation? for weight fraction, Wx equals to x into p to the power x minus 1 into 1 minus p whole square. So, this is the expression, and your x, you are looking for trimer. So, your x is 3 and your p is 99%. So, it is 0.99 square into 1 minus 0.99 square, and it will be approximately 2 point. I have worked this out. So, to save some time, I do not want to calculate it again, serves no purpose. So, these are some of the very simple problems that you can tackle with this. It is also informative, and you can find out also for yourself that what will be the number fraction for a dimer, trimer, so on and so forth. You will find that some of them are higher than the big polymeric species. However, the big polymeric species actually contribute more in terms of weight, much more in terms of weight, rather than some of these very small species. That is more evident when you are plotting the weight fraction as a function of the x. So, we will stop here, and in the next class what I want to discuss is a particular site reaction that could be detrimental to the processing to the process of step polymerization, and then finally we will talk about interfacial polymerization, because that is also an important industrially used process. So, thank you for your attention in this class, and see you in the next class.